All righty then. Good morning. So, people are still filing in. I probably should set this up some way where I don't have a waiting room, but I haven't investigated that yet, so I'm not sure how to do it. But I'll have to figure that out, make myself a note or something. And I want to get rid of that. And share. Okay. All righty. I think you can see that plate. So this is where we stopped our discussion more or less the last time. We were talking about rate laws and how you can mathematically model the effect of concentration on the rate of any reaction using experimental data. And so we talked about this one in particular, how you can use the eyeball method to say, oh, okay, we have all these experiments, and I see that if I just look at experiment 1 or 2, the concentration doubles, the rate quadruples, so it's second order. And then we mentioned, well, what if it's not so easy to see? You can use this ratio of the rate laws that are general and deduce it that way by solving for the exponent using the law of logs. Then we also talked about how you can find K for each one of those experiments, that rate constant, and then take the average and get the best K value, or you can just approximate a K with one experiment by plugging in. So that's pretty much where we left off last time. Any questions on that? All right, then this is kind of a different area we're going to get into now. The question is, okay, we see our rate laws here, and this tells us how the rate of a reaction is related to the concentration of reactants. But the question is there any equation that could come out of what we talked about so far that would allow us to track changes in concentration in time, as an experiment goes on? In fact, my class started the first lab yesterday, and they did Beer's law analysis where they experimentally track the change of concentration of a reaction of blue dye with bleach in time. So what we want to look at next is those type of equations. And so do they exist? Yes, they do. And they actually come out of these equations that we looked at already, the rate laws. And they're called integrated rate law. So if you use calculus on these equations, now let me take you through this table here. The first column is the order. We have 0, first, and second. So let me ask you guys to see if you're still awake out there. Are these the only possible orders you can have for reactions?
No.
Yeah, that's correct, guys. Good. So you know that orders can be anything, not just these, but in a second semester general chemistry course, we often use these three orders just as representative. So that's the first column, 0, first, and second. The next column are the rate laws themselves. So it's the rate, which is always in molarities per second. That would equal for zeroth order, this for first order, it would look like that because you have a power dependency of 1. And then, of course, the last one, power dependency of 2. And you see how that rate constant, the units of that change for those. And so you kind of get a flavor for the rate constant and its units. All right. The third column is what we're interested in today, and this is the integrated rate law. And we'll get into a little bit in the next few plates how these rate laws are derived through calculus. But let's just take a look at them and see if we can apply our mathematical knowledge in understanding what each term is. So for the zeroth order, for example, this zeroth order equation here, it tells me that the concentration of reactant A at time t, that's what that subscript means. So in that equation, I have concentration of A at some time t, and that's usually a time in the future. That's opposed to this term right over here. Does anybody can guess what that concentration refers to?
The original concentration.
Absolutely. That's the initial concentration, or the concentration at time equals 0. So that's when you start the experiment. That's when you set it up. You have all these initial concentrations of your reactants, and that's the time 0 concentration. So you see in the equation that the time t is the time that the experiment has run. And the concentration at that time is denoted in this way. For zeroth order, that should equal some rate constant. That's the familiar rate constant that we've been talking about. It should equal minus kT. That's the time that the reaction has been running. So again, this term up here is a concentration, so that has units of molarity, but it's a particular concentration. It's at time t. This is actually the time right here. So this would be, say, the concentration at 10 seconds, and then that would mean that this t is 10 seconds, and so forth. So each one of the orders has a different mathematical function that describes how concentration would change for a reaction of those different orders. Any questions on that so far? So we're kind of getting into math a little bit here. All right, so that means we can track changes of concentration in time. What I want to point out about this form of the integrated rate law for all of these, they're essentially infinite point functions. So you give me a time, and it could be any time. Just make up a time. It could be 2.35 seconds. Then I can calculate the concentration of that reactant A at 2.35 seconds. If I have the rate constant for that particular reaction and the initial amount of reactant. And I can, like I said, I can pick any time. Now, you guys probably are used to a functional form like this. where y is the dependent variable and x is the independent variable. In other words, you pick an x and you can determine y. So it's just kind of like all of these equations that we're looking at. Namely, for the first one, y would be the concentration of A at some time, and x would be the time. And you see that for zeroth order, that functional relationship would be a straight line, y equals mx plus b. And so b, that y-intercept right up here, does anyone know what that corresponds to for zeroth order?
It'd be the concentration at 0 seconds or 0.
Yeah, that's right, because this is in the form of a straight line, y equals mx plus b. So b is associated with this term, x is the t term, the slope is minus k, and y would be the concentration. So if I went to lab like the students did yesterday, and they set up an experiment that allowed them to track the concentration as time went on, then I could make a plot like this and see if it's linear, if it comes out to be a straight line. And if it does, then I know that for that particular reaction, the order is zeroth order.
Professor, I know I came in a little bit late, but for the half-life equation for the first order, where do you get the 0.693 in the numerator?
Okay, that's awesome. Well, I'm just getting to that column, so you haven't, you may have come in late, but you're in time.
Okay, thank you.
Yeah, no problem. Okay, good. So we're going to get to that next. I'm just kind of easing everybody into these integrated rate laws and what the terms mean for each one. Like for the first order, if the reaction was first order, then what would I plot to get a linear function? Anybody?
1.
It would be the natural log of the
Yeah.
concentration.
Very good. So I put natural log of the concentration here versus,
Time.
yeah, you guys are good. Awesome. So this is my y, and there's my x again. And for the second order, what would I plot to get a straight line?
Two natural log of the concentration of it.
Actually, for second order, this one, I would plot this 1 over concentration versus time. Right? So I don't know if you can see this. I'll put it over here because I got my thing in the way. So it would be 1 over concentration versus time. That's what I would need to plot for a second order reaction. But reactions, I'll just pick A going to B. So as soon as I write that down, I know the form, what that rate law is going to look like. And whatever X is, that's what it is for every time you do an experiment involving this reaction. So in other words, for reaction 1, X is, say, 0, then if I do another reaction 2, X has to be 0 again. It can't change order because you haven't changed your reaction. And that's why it's the law. It's the rate law for this particular reaction. So you can only have one. It's like the Highlander. If you guys remember that movie from about 20 years ago, there only can be one. Anyway, it's a stupid joke. But if this turns out to be linear, this first plot, then this can't be linear. It's got to be something like that, and this is going to be something curved. Is that clear?
So what you're saying is like once you get to first and second order, you're not going to get linear graphs.
No, that's not what I'm saying. I'm saying that if this reaction is 0th order, this hypothetical reaction that I just made up, if it turns out to be 0th order, then this plot has to be linear and these guys have to be curved. Now, say I look at a different reaction. Let's say I look at C going to D. I know the form of the rate law is going to look like C to some power. And say now this power turns out to be 1, first order. And when I plot this, when I plot the concentration versus time, this guy is going to be curved. When I plot ln, concentration versus time, this is the one that's going to be linear. And then 1 over concentration versus time, that's going to be curved. So this guy's the linear one. Is that understandable? Am I completely missing the boat on trying to make this point?
It
Yeah.
makes sense.
Will the order keep going up like to infinity? Like, is there going to be a third, fourth, fifth order?
Yeah, these orders can be anything, and they can even be negative. So it's possible that these are negative or fractional, 0.537. But in freshman general chemistry, second semester, we just deal with these ones because they're representative. The other ones you can do later if you do research in kinetics. So back to that thing that I was talking about. Is this clear, or are there any questions on, when you have a reaction, then it has a specific rate law with a specific order? And these integrated rate laws tell you the behavior of how the concentrations will change in time for each different order. So I'm just going to point that out. If you have any questions, ask, but you should think about that and study it and kind of understand that, because part of the online activity for your lab, that first one, you have to determine the order of some reaction given data. And the data that you're given is just the concentration and time, right? If you look at that OLA 1, the online activity for lab, and it tells you to generate other columns over here, like the log of the concentration, 1 over, oops, kind of went right past. Okay, and so forth. And it only gives you this experimentally, and then it asks you to determine the rate law. So what they're asking you to do is make plots. Make these 3 plots, because we're going to just assume that for Chem 201, it can be 0th, first, or second. So you have some experiment where A is going to something, and this is the concentration of A and how it changes in time. So what you're going to do is you're going to make these different plots up here and see which one comes out linear. And I think for the data that you have in lab, it's going to be like this over on this side, where the log of the concentration versus time comes out linear. So you say, oh, because that's the behavior, I know that the integrated rate law predicts this behavior for first order, so X must be 1. And so that's how you're going to come to the conclusion. So when you study that and you do that OLA 1, keep that in mind.
So whichever one of the 3 graphs comes out linear tells us that order.
Absolutely, you got it.
Okay.
And there can only be one. The other guys are going to have curves in them.
Oh, okay. I guess because I was confused at first because I previously understood that like the 0th order integrated rate law only did linear, and then like the first one only did that curve going down. But I guess it's just when we graph them 3, the one that comes out linear tells us the order.
Yay, you
Okay.
got it.
Thank you.
Yep. So that's kind of a point that can be confused. And so you have to think about it, work with it, and know it, because you're going to be given some reaction and you don't know the order. But now you have 2 different ways to determine that order. Remember the one we just looked at, well, the last few conversations, we used experiments. I call that the tabular method, or the method of initial rates, where you just look at the initial conditions, you find the initial rate for a whole bunch of experiments, and then you use that ratio of rate laws, or you can use the eyeball method to get X. This graphical way, using the integrated rate law, is a second way to determine the order dependency. Does that make sense?
Yeah, it makes sense.
Okay, cool. All righty, so now we're going to get to this half-life equation. And you see that what this half-life equation is, it says T1/2 right here. This equals, for 0th order, the initial concentration over 2 times the rate constant. For first order, it equals 0.693 over the rate constant. Doesn't have any initial concentration involved at all. For second order, it equals this half-life, 1 over K times the concentration initially. So what is this half-life equation? We should probably define that first. Does anybody want to take a crack at the definition of T1/2?
The time it takes for half of the substance or molecule to either be used up or decompose.
Yeah, that's it. Exactly. So it's it's the amount of time to cut that initial concentration, A0, in half. And that's all it is. So remember what I said about these integrated rate laws over here for 0th, 1st, and 2nd. These integrated rate laws are really infinite functions. So for each one, I have a lot of writing over there, so let me write for 0th order, just as an example, down here. So I can pick any T, and that'll result in a different concentration at that time, right? So it's an infinite point function where this is my X, and this, I'm sorry, that's my Y, and this is my X. So I can have an infinite number of XY points. Okay. What this equation is here is just one of those points. And it's a particular point. It's the time that it takes to cut this concentration in half. Get this out of the way. Okay, so I'm going to cut that concentration in half. So this infinite point function folds into one point. So what I should have done was to put it on a new piece of paper. Okay, so sorry, let's go back to that equation. T equals minus KT plus A0. So that's an infinite point. Now I want to look at just the half-life. When that concentration is T 1/2. That's going to equal 1/2 the initial. Right? That's the one point that I want to look at. So I'm going to make that substitution into the infinite point function. So 1/2 the initial equals minus K. Now this is a particular time. It's not any time. This is T 1/2. And now I can solve for that T 1/2. So if I solve for T 1/2, I'm going to have minus K T 1/2 equals 1/2 A0 minus A0, right? And so this is going to equal a negative half of A0. And this is still the same over here. So T 1/2 equals A0 over 2K, right? Does everyone see that? And that's what we find here. So to answer your previous question, where does that come from here? I just plug in the same for that one. And the half-life comes out to be 0.693 over K. Do you want to see that one done?
Yes, please.
All righty. So let me go back to here. All right, for first order, the the equation is ln concentration equals minus KT plus ln A0. So half-life, I'm going to make that substitution. ln 1/2 A0 equals minus KT 1/2 plus ln A0. I could subtract that from both sides. So I get ln 1/2 A0 minus ln A0 equals minus KT 1/2. And then I know that when I take the log of something minus the log, one of the law of logs says I can put that in the denominator. So I can change this to ln 1/2 times a0 divided by a0. That equals minus kt 1/2. These guys cancel out. Guess what the log of 1/2 is?
I see.
Yeah, said the blind man, but he did not see it all. Okay, so yeah, now I solve for t 1/2, and that equals 0.693 over k. And that's what we got here. And you guys should do it for second order and see that you get this. Now, what's interesting about the half-life of these different orders? For first order, the more that you start with, the longer it takes to reach the half-life. For first order, it doesn't matter what you start with as far as concentration, it always takes the same amount of time. It turns out that radioactivity, all radioactivity, I can't write and talk at the same time. All radioactivity is first order, so this goes into carbon dating and dating rocks and the age of the universe and stuff like that. And for second order, the more you have, the more you start with, the longer it takes to cut it in half. I'm sorry, not the longer, the shorter it takes, because it's inversely proportional to concentration. So that's kind of an interesting thing. All righty. Now, the next few plates, I don't think, I mean, they're important, but they're not as important as this plate. I think it just goes on and shows you where these were derived from. For example, and this is just for people who have calculus, you're not going to be tested on any of this stuff. So for, say, a first order rate law. So here's our first order rate law. Rate equals k times the concentration to the 1 power. I know that that rate equals the change in the concentration of A over the change in time for this reaction of A going to whatever, because there's a stoichiometric coefficient of 1 there. So I can take those two and equate them. This rate equals this rate. And I do that over here. And then I use integration. I integrate, well, first of all, I have to clear like terms. I got to bring this over to this side. I got to bring this concentration over to this side. And then I'm going to integrate through concentration space, for those people who know that, 0 to some concentration in the future. And on this side, I'll integrate through time space, t0 to some t in the future. And when I do that integration for first order, what pops out, voila, the integrated rate law for first order. So that's where that comes from. So I just presented it here back in that table that we talked about on the previous slide. I just gave you all of these rate laws, and I didn't tell you where they come from because you don't have to know calculus for this class, but people who do know calculus, that's where it comes from, that integration. All right, so what else do we have? I keep going the wrong way here. Oh, geez. Having some technical difficulties. I have to. Reopen that, I think. Oops. Wow, this is really not helpful. Thanks for bearing with me. So here we go. Are there any questions on any of the stuff that we talked about so far?
No.
Okay, good. We really chopped up that plate, but like I was saying, this is the integrated rate law for first order, and it shows that, for example, if you plot the log of the concentration versus time for a first order reaction, if it really is first order, then you're going to get a linear function, whereas the concentration versus time is going to be curvature. It also shows you kind of the half-life idea here, is it doesn't matter whatever you start as far as concentration, it always takes the same amount of time to cut it in half for first order. So in other words, if I start with 150, half is 75, and that time is T1 half. And then half of 75 is 37.5, and that takes the same time. And that comes out from that equation for first order, because it's concentration independent. Okay. Now this is the second order stuff. And again, we go back to the rate law, the second order. I know that that has to equal minus delta A over delta T. I integrate through concentration space again, time space, and I get this integrated rate law. Okay. This shows you the behavior for first order. No, I'm sorry, second order. So if I plotted concentration versus time, it would be curvature. If I plotted the log of the concentration versus time, it's going to be curvature. But if I plot 1 over concentration versus time for a second order reaction, that's where I get the linear function. And there's our half-life for second order.
I have a question.
Go ahead.
So with these laws, would we ever be asked to do something with 2 reactants or just 1?
Yeah, you might be. For example, in the first experiment that 1/3 of my students did yesterday, you're going to have a reaction between. Let me pop up a clean page for this one. All right, let me get this. So for this reaction, you're going to have dye. It's just food coloring plus bleach. And the bleach is NaOCl. So that's going to go like that, right? So as soon as I write down this reaction, I know the form of the rate law. It's going to be rate equals the rate constant times dye to some power times bleach to some power. So when you have two reactants, how do you use the graphical method to deduce one of those power dependencies? And that's what you're going to be asked to do for this first lab. Well, what you need to do is read the background section in the lab, because it talks about the method of isolation. And the method of isolation, what it does is it isolates the effect of one of the reactants on rate, so you can use the graphical method. How does it do that? Well, in the experiment, you make the concentration of bleach much larger. This is in excess. And this is the limiting reagent, the dye. So the dye is so small, so when you run these reactions, essentially, by the time the dye runs out, the bleach, which is in excess, its concentration, it goes down a tiny bit, but it's pretty much the same. So if it starts out at 1 molar, it might end up at 0.999999, you know, whatever. It's pretty much constant, right? So its effect can be incorporated into this constant. You could rewrite the rate law as this K for experiment A, let's say, times dye to the X. And so when you take your experimental data of concentration and time, you're just going to do it for the dye, and then you can make those plots. Let's put time over here instead. You can make the plots ln concentration and 1 over concentration. So you make the 3 plots that we just talked about, and you'll see that one of them's linear. You're going to see that it's this one. And so you're going to be able to deduce that x equals 1 for first order, because the log of the concentration versus time plot came out linear. So that's one way of doing it for reactions with more than one reactant. It's called the method of isolation, where you can experimentally do this trick where you flood in the concentration of one of the reactants, so its concentration is pretty much constant. It can be incorporated into the rate constant. So I don't know if that was more than you bargained for, but I think that's the answer to your question. Does that make sense?
Yeah, it makes sense. Thank you.
Yeah, okay, so it can be done. And you're going to get into that too. So it was a really good question. All right. So we're moving right along here, I think. And now we switch gears into another related topic. Okay. So far in our discussion, we've talked a lot about how concentration affects the rate, but we left all those other factors like a catalyst, temperature. We left that unexplored, and those other factors in our mathematical equation have to be embedded in this proportionality constant, which we called the rate constant, right? Because we left everything else constant. The only thing we allowed to change in our discussion and in our experiments is the concentration. So we were able to deduce its effect the concentration changes its effect on the rate. But how about those other things? What if we want to explore the effects of the other parameters that are embedded in that rate constant? And that's what we're going to do next. So in this plate, it kind of introduces us to that and temperature. So here is the rate constant for a reaction, this reaction up here, versus temperature. And we see that for this particular reaction, that K is not a constant with temperature. In fact, it blows through the roof here. It changes exponentially with temperature. So how can we understand this, and how can we mathematically model that change? And so that's what the next few slides are going to talk about. And the way to understand that, at least conceptually, is to use what's called the collision model. And it's a very simple model of how reactants come together to react to form products. And so what the collision model says, okay, say I have two reactants. I have this reactant here. It's maybe a homonuclear diatomic, and this reaction here. I don't know, let's call it H2. No, yeah, let's call that H2, and let's call this F2, something like that. Now, if they hit, will they react or not? And so collision theory says, okay, for reactants to react, they have to at least come into contact, right? So when they collide, will they react? And what are the parameters that affect their reaction? So the collision theory is very simple, and it explains that at higher concentrations, there would be more collisions. So for most reactants and reactions, you would expect that when concentration increases, the rate of the reaction increases. So collision theory says, it explains that simple thing. Also, it starts to get in some temperature effects here. At the higher temperature, you expect the molecules to move and bounce off the walls quicker. So even if it's a unimolecular reaction, it's got to hit the walls of the container, at least, or maybe another molecule in there. And the higher the temperature, the harder it hits, and it has more energy to react. So that should increase the rate of the reaction. So that at least initially and at first glance, that makes sense. So the question is, when they collide, will they react? And the answer is, well, maybe. Sometimes they will, sometimes they won't. So what is the factors that we should look at to tell us when they will and won't? And so if you think about it after a while, you'll say, well, it must be sometimes when they hit, they don't have enough energy and they just bounce off each other and they don't react. So the question is, what do they need the energy for? Anybody?
To break bonds and form new ones.
Awesome. Yeah, so these guys are bonded. So you have to break them. And that's why there's an initial amount of energy that's needed in a reaction, because you got to break old bonds and form new ones. And that's pretty much chemistry. Does a reaction happen? Because chemistry talks about reactions. Does a reaction happen? Well, what happens in a reaction? Well, the bonds in the reactant are broken and new bonds are formed. But if you don't have enough to break those, then there's no reaction. So thinking about this, scientists and Arrhenius thought about this a lot. He proposed a name for that energy, and he said the minimum amount of energy needed for a successful reaction, let's call that the activation energy. And that energy goes into breaking bonds. This also implies there must be an energy release once new bonds are formed. So he's thinking about this, and he wants to come up with a picture to understand that. So he writes, he proposes something like this. It's a potential energy, kind of a surface, and it's a plot of energy of a reaction and how that energy changes as the reaction takes place. Okay, so that's your X and Y. Energy on the Y-axis, X is kind of as the reaction takes place. It's sort of like time, I guess. So over here, at a certain energy, I have the reactants. And over here, at a certain energy, I have the products. So as soon as I look at that, I know whether this reaction is endo or exothermic. Anybody?
Exothermic.
Yeah, you can read. Sometimes I can't read, but yeah, it's exothermic because this guy's higher energy than this guy down here, the products. And when I take the difference, which is always final, this is the final minus the initial is going to be higher. I'm going to get a change in energy for the reaction that's negative. That's delta H, that's heat energy. And so that tells us there's an exothermic reaction. If it was endothermic, then, maybe it goes through a barrier height and ends up, say, up here. Now, this final value is higher than the initial value. And in that case, delta H is going to be positive. But in either case, you have to go through this activation barrier. And so Arrhenius he's defining this activation barrier. What's it used for? It's to break the bonds of the reactant. So in this reaction, you see it's just a unimolecular reaction. That's one molecule, and it arranges from this reactant where I have a nitrogen connected to a methyl group, and the product now has that methyl group connected to the carbon. So they're two different molecules. It's a unimolecular reaction. And I need to break bonds while at the same time forming the new ones. That is what Arrhenius calls the minimum energy or the activation barrier, because you're going to get energy as the new ones form. So this has to be the minimum amount that's required for a successful reaction. If you want to propose the activation geometry, or what's called the activated complex, then your guess would be an average between the reactant geometry and the product geometry, where you have a simultaneous breaking of the carbon-nitrogen bond, while at the same time a formation of the carbon-carbon bond in the product. So if you're asked in a test or in homework to propose what an activated complex would look like, or a transition state geometry, that's what it's sometimes called, you would want to keep that idea of Arrhenius in mind and propose something that's in the middle of the reactants and the products, something that has the new bonds being formed while the old ones are being broken. Okay, does that sound reasonable?
Yes.
Yeah, you guys still there? All right. You know, this is probably not a bad time to break, and because we went through a lot of stuff, I think, for this, and maybe we could take a look at the homework, a quick peek, and see how the stuff we learned today can help you answer some of those homework problems. What do you think?
Yes.
Yeah.
Yes, please.
All right, cool. So I'll get
Sounds
rid of
good.
this. Very good, very good. So I'll get rid of that. And I need to take a look at this here. This is our homework. I thought it was going to be really cool and get everything ready for us so we could just go and do some problems, but turned out to be messy. Let's get a new one of these just in case. So you guys have been working on these first few problems here on rate laws using the tabular method. We got a whole bunch trying to relate those to the generalized rate equation. So more of the same. Oh, now we're getting to what's the units of the rate constant? Yeah, so we talked about that and how they change so that rate equals molarities per second. Still some more order stuff. Rate law. Ah, here we go. Question 14. This is the material that we looked at today. So this one asks, it says, there's a first order reaction and it's 45% complete at the end of 43 minutes. What's the length of the half-life of this reaction? All right, well, they tell me that it's a first order reaction. And so for number 14, it's first order. So I know that the rate equals K times the concentration to the 1 power. I also know that the integrated rate law looks like this. Because it's first order. And I also know that the half-life equation equals this because it's first order. At the end of 43 minutes, it's 45% complete. What is the length of the half-life of this reaction? So what I would need to do to calculate the half-life is to find the rate constant, okay? How can I do that? How can I find the rate constant given that little bit of data? Does anybody know what I should do?
Professor, I have a question. Is 0.693 is it negative or positive?
I think it's positive.
Okay.
Should I pop it back up on the table? Either I have to derive it again, just plugging in like we did before. I think I erased that though. Or I can look up on this PowerPoint. There we go.
Actually, I remember it was shown as a negative.
Oh, there it
Oh,
is.
wait.
Positive.
Oh, never mind. My bad.
No, that's cool. Thanks for checking on me because you know you mess up one negative could ruin the whole day.
Yeah.
Okay, good. So what you're going to need to do is somehow use this this information over here, the 45% complete, and you have to use it in this integrated rate law for first order. And to do that, you really have to be comfortable with these definitions like we went over. Okay, so let me show you how you can use that, and then I'll let you finish the problem and figure it out. But I just want to point out the thing that you have to do to solve this. Now it says 45% complete. Now I know I can use the law of logs to rearrange that integrated rate law. Remember, for example, the ln of y minus the ln of x equals ln of y over x. That's another one of those law of logs. And if you don't believe me, just pick a number for y and x and calculate its value, and then calculate the value on this side again using the same y and x, and you'll see that they're equal. Anyway, I'm going to use that law to change the integrated rate law from this form to this one. Check it out. ln a over t divided by a 0 equals minus kt. So what I did was I just subtracted this from both sides, and then I incorporated it in the bottom just like I did over here. Okay. So anyway, this is another way to look at that integrated rate law for first order. Any questions on that? All right, so far so good. So this tells me the concentration at time t divided by the initial concentration. Does that equal 45% or 0.45 or something like that? So you think about it for a while, and after you get comfortable with the definitions, you're going to say to yourself, no, it doesn't. This is the concentration at time t. So if I divided by the initial concentration, this fraction equals the fraction that remains. They're giving you how much is complete. So what is the difference between that? The fraction that remains and the fraction that's complete or reacted, another way to say that. So if 45% is reacted, how much remains?
55.
Thank you. So the ln of 0.55 equals minus k times 43 minutes. I can solve for k, and if I can solve for k, then I can solve for the half-life. Any questions on that?
No.
Okay, cool. Does that make sense?
Yes.
Okay, cool. All right, so that's the kind of stuff you're about to get into now. How exciting is this? Here we have reaction A goes to B and C is known to be a 0th order in A with a rate constant of that at that temperature. An experiment was run at that temperature where we have an initial amount of the A. After 5.0 minutes, the rate is. All right, so I know that for this problem, I'm going to have to use the set of equations that correspond to 0th order. So to answer this question, I'm going to be using a different set of equations than I did on the previous one. I'm going to be using rate equals k, because 0th order. And I'm going to be using the integrated rate law for 0th order that looks like this. Okay. So that's your hint for that one. Then here we have this reaction exhibits this rate law, so it looks like it's second order. They give you the K. This reaction is run where the initial concentration is that. What is the half-life for this experiment? So for this problem, you're going to use these equations, which correspond to the rate law for second order and the integrated rate law for second order. Okay. And so again, and then I think there's just more practice of the same kind of ideas. And that's it. So if you get through problem 18 after today's talk, then I think you're in really good shape. Any questions on anything? All righty then, I will, or I'd like to stop talking about stuff now and just let anybody hang out who has any questions, and then we can deal with your questions. I'm going to pack up this and I'm going to stop the